So the main difference about this activity is that now we understand our function as a formula and then later as a graph. The previous activity, we understood our function because we had a table of data points, right? So it may be helpful, and I would kind of do this if I had to do this problem. It may be helpful just to turn your function into a data table. For example, in this part A, we could make a table of values for my function where the x's included all the different x values that we might be asked to consider here, 0, 1, 2, 3, and 4. And if you do sort of front load all of your arithmetic computation for the values of the function, called q of x here, right, that can maybe help to streamline your life. Right? How do I get the values of q of x if I know the values of x that I want? What's the link? How do we understand this function? Exactly. We know the x values. We have a formula that describes my function, so I just have to put those x values into my formula. For example, q of 3 is 4 minus the quantity 3 minus 2 squared. And so we do out that arithmetic. 3 minus 2 is 1. 4 minus 1 squared is 3. And so we get a 3 here. I'm going to try again to use colors to keep us straight on what's what here. Right? And so if you get that whole table of data first, then you can treat this problem just like the previous problem that we did and get your average rates of change out of that table of data. In this question, you're asked to take a couple of functions, q of x and h of t, that we see the graphs of here, and compute some average rates of change. Let's compute one really quickly that wasn't asked for. If I look at the q function, say I wanted to know what was the average rate of change from x equals 1 to x equals 4. So how would I compute that? I would have to divide, in the numerator, I would have to divide q of 4 minus q of 1. And in the denominator, I would have to divide 4 minus 1. So I would look in my table here, right? I would find q of 4 right here. Right? I would find 4 itself matched up with it, right? So I would have a 0 and a 4 going into my formula there. So 0 on top, 4 on the bottom. Q of 1, I would find where? What would Q of 1 be? 3. You can find it right there, right? So I'm going to get my 3 sitting right there. And then I have my 1 come from the other side. Subtract those, do my division, negative 3 on top, positive 3 on the bottom. I get negative 1, right? So there's my average rate of change of this function on the interval from x equals 1 to x equals 4. So the question is, what is it about the graph that is equal to negative 1? How do I locate that number negative 1 on this graph? How do I spot it? What does it correspond to? How do I visualize an average rate of change? It's an increase or possibly decrease, right? It's the rate at which the output of this function is increasing or decreasing per every unit of increase or decrease in the input, right? Taking a look at how we compute an average value, I'm subtracting a pair of y's, right? 0 minus 3. This numerator, this negative 3, let's keep color coding here. This negative 3 that I get on the top, I would find that in my data table as just the difference between my two y values, right? Minus 3. 3 minus 3 is going to give me this 0, right? The denominator, 4 minus 1, positive 3. Where do I see that? It's the difference in my x values up on top, right? So I'm subtracting y values, I'm subtracting x values, and I'm dividing the former by the latter. What kinds of quantities do we get when we take and subtract y values, and then we divide them by a difference in x values? y2 minus y1, x2 minus x1. What kinds of quantities are those? They are slopes. Exactly. So every average rate of change is a slope. But the question is, slope of what? It's a slope of a line. So first thing we need to know, especially as practitioners of pre-calculus, is that only lines have slopes, right? Points don't have slopes. Numbers don't have slopes. Functions don't have slopes. Curves don't have slopes. We can talk about that in calculus a little bit, but even in calculus, we still want to take that curve and turn it into a line and then find the slope of that line. So it's the slope of which line? Which line has a slope of -1 in this example that I just computed? Where would I find that line?
Line that goes through 4, 0.
Yeah, it's the line that goes through these 2 points on my graph. After all, when I compute the average rate of change of a function, that's the only information I use. The coordinates of one point and the coordinates of another point, right? The coordinates of the point here at 1, 3, the coordinates of the point over here at 4, 0. Those are the only pieces of information that I used to compute my average rate of change. And so the line that I've computed the slope of must be the line that connects those 2 points on the graph, right? That line right there has a slope of -1. And that is what the average rate of change tells us on a graph. The slope is equal to AV of 1, 4 equals -1, right? So let's talk about part D together, even if you didn't get a chance to get to it in your groups. So for the function q, the average rate of change on the interval from 0 to 3 is equal to 1. And again, where would I find that number 1? What's equal to 1 in that example? So this 1, which is the average rate of change from x equals 0 to x equals 3, is the slope of this line that joins the point at x equals 0 with the point at x equals 3 on the graph of my function. And so let's take a look at the question. Since the average rate of change on the interval from 0 to 3 of this function is equal to +1, the assertion is, therefore, this function is increasing on the interval from 0 to 3. What do you think? True, false? If I read this question, is the function q increasing on the interval from 0 to 3? A lot of you said you were leaning towards true. So what's the argument? Why can we make an argument that this function is increasing on the interval from 0 to 3?
Well, if you look at the rate of change between 1 and 3, it's positive. So
Rate of change is positive, right? And we remember that anytime we have a line with a positive slope, that line is going up on a graph as we look at it from left to right, right? So there's a good argument for the true case, right? Positive slope tends to mean increasing, right? So why am I so insistent that there's also an argument against true, that there's an argument for false here? How could we say that this is not in fact increasing? So you're saying when we read the question again, the question is not whether or not this line that we drew is increasing between x equals 0 and 3, because that's definitely true, right? The question is whether we can say that the function q is increasing, the function whose graph is this blue curve. Is that function increasing from x equals 0 to x equals 3? If we cue in on, pun intended possibly, the behavior of q, we see that q, as we ride the graph, is definitely increasing. It's going up from left to right, right? Until we get here, the point 2, 4, and then suddenly the opposite starts happening, right? So between this point here, 2, 4, and this point 3, 3, if I asked what was the average rate of change between those 2 points, I would get the slope of a different line. I get the slope of the line that connects those 2 points. That slope is going to be a negative number, yeah. So that line, in fact, has a slope of -1. I'll let you sort of compute that if you want to, right? So between the point x equals 2 and x equals 3 on this graph, the function, in fact, looks like it's decreasing and not increasing. So there's an argument on both sides of this. I think a lot of the questions and the activities are kind of posed like that. Anytime there's a true-false, this is the kind of textbook author who doesn't necessarily throw in with either one, true or false. I'm more interested, and he's more interested in, what are the arguments on both sides of this, right? And can we make this? Are there ways of sort of clarifying what we mean here? So, are there ways of making an accurate statement here about whether q is increasing on the interval from 0 to 3? Let's sort of write it out. So let's make the argument for true again. Q is increasing from 0 to 3, but I would add in the words on average. After all, the rate of change that we computed was an average rate of change. And so on average between x equals 0 and x equals 3, q is increasing. Right? Because if I look at where I started and where I ended up, I definitely have increased my y value as I increase the x value, if that's all that I look at. But if I look at everything else that happens in between, I see that there is a place, there's an interval of x values, right, from 2 to 3, where in fact q is not increasing on that interval. So what we can say there, I suppose, is q is not always increasing. Maybe it's kind of a way to frame that. Not always increasing on the interval from x equals 0 to x equals 3. Right? Because there's this place where, in fact, the average rate of change is negative between these 2 points. And so the function is, on average, decreasing between x equals 2 and x equals 3. Right? So that's the kind of nuance that we need to be able to bring to our understanding of functions, because when we get into calculus, next semester, when you're taking a calculus class, you will be able to make these ideas about increasing and decreasing even more specific, right? Using formulas and instantaneous rates of change, not just average rates of change on an entire interval, but instantaneous rates of change at a single point. And so you'll be able to say, for example, that my function is increasing at x equals 1, right? And it's decreasing at x equals 4, right? Instead of having to speak about an entire interval. But we don't have in pre-calculus the ability to compute that yet, because we need different techniques. Those techniques are going to build exactly on this one when you get to calculus next semester. So the first thing you do in calculus when you start talking about whether a function represents an increasing or decreasing trend, you start with this idea again, the average rate of change. And then you say, well, how do we make the 2 points that are necessary to define the average rate of change converge into a single point at which we can compute an instantaneous rate of change? And that part is the magic of calculus, for which you're going to have to beg a semester's worth of indulgence to see that again in your next course.